Above the war-torn skies of Europe, the B-17 Flying Fortress was a symbol of American might, until some of them simply vanished. Not by enemy fighter, not by flak. Just sudden, catastrophic explosions that left no trace, no explanation, only the chilling question: what invisible enemy was tearing these giants from the sky? For months in 1943, the Allied High Command faced a terrifying anomaly. Alongside the brutal cost of combat, dozens of these meticulously engineered warbirds were disintegrating without warning, their crews lost in fiery balls that defied logic. A silent, internal predator, hidden deep within their metallic hearts, was claiming lives and sowing terror, and no one knew why. Before we unveil this incredible wartime secret, tell us in the comments, where are you watching from today? This is the untold story of a detail so small, so seemingly insignificant, that it almost cost hundreds of lives and changed the course of the air war. The frigid dawn of October 14, 1943, began much like any other at Royal Air Force Station Thorpe Abbotts, a sprawling patch of concrete and corrugated iron swallowed by the East Anglian countryside. The air, thick with the smell of aviation fuel, damp earth and wood smoke from the barracks, bit sharply at any exposed skin. Overhead, the sky was a canvas of steely gray, promising little warmth. On the distant runways, the guttural roar of Pratt & Whitney R-1830 twin Wasp engines and the deeper, more resonant thrum of Wright Cyclone engines already vibrated through the ground, as crews prepared their B-17 Flying Fortresses for another perilous mission into the heart of Fortress Europa. The sound was a constant, a grim symphony that underscored the relentless rhythm of war. Inside the cavernous maintenance hangars, the atmosphere was a mix of intense focus and organized chaos. Technicians, their faces smudged with grease, moved with practiced efficiency around the massive bombers. Technical Sergeant Raymond Parker, a man whose hands bore the indelible marks of a life spent in meticulous mechanical labor, was engrossed in his work. At 23, Parker possessed a quiet demeanor, but his gaze was sharp, missing nothing. Before the war, he had been a tractor mechanic in Iowa, a profession that demanded an unwavering attention to detail and an innate understanding of how complex machinery functioned, and often how it failed. His experience was not merely theoretical, it was tactile, rooted in the tangible reality of metal, wires, and fluid. This background, far removed from the battlefields, had paradoxically prepared him for a critical role in the war effort. His current charge was a newly arrived B-17 Flying Fortress, its aluminum skin still bearing the factory-fresh sheen from the Boeing plant in Seattle. These bombers, the backbone of the United States 8th Air Force's strategic bombing campaign, underwent thorough pre-flight inspections before being committed to active duty. Parker worked methodically, a flashlight beam cutting through the hangar's filtered light, illuminating the intricate internal architecture of the aircraft. He moved into the bomb bay, a narrow cylindrical space that, in a few hours, would carry thousands of pounds of high explosives towards German targets. The bomb bay was a labyrinth of hydraulic lines, pneumatic tubes, and, crucially, electrical conduits. Each component was essential, each connection a potential point of failure. Parker's inspection routine was exhaustive. His fingers, accustomed to the subtle nuances of mechanical systems, traced the path of a critical wiring harness. This specific bundle of wires was instrumental. It carried the 28-volt current necessary to actuate the bomb release solenoids, simultaneously transmitting signals to the bombardier's control panel. According to the highly detailed schematics provided by Boeing, this harness was designed to follow a carefully defined route, protected by rubber grommets and secured within metal conduits, keeping it isolated from any moving parts. As Parker's fingers followed the wire, a subtle anomaly registered. The cable felt unnaturally taut, stretched beyond what seemed appropriate. He paused, his brow furrowing slightly. This was not the smooth, relaxed curve that the blueprints depicted. He repositioned his flashlight, angling it to better examine the specific section of the wire. It was clear. The wire was under significant tension, pulled taut to bridge a gap, deviating from its designated, protected path. Instead of passing securely through its conduit, it was now making contact, albeit lightly, with the sharp, unforgiving edges of the bomb bay door's hydraulic mechanism. Parker retrieved a small, calibrated ruler from his toolkit. With precise movements, he measured the discrepancy. The wire was exactly 3 inches, or 7.5 centimeters, too short. This was not a manufacturing oversight that resulted in a loose wire, but rather a short one, demanding it be stretched to reach its terminal. This seemingly insignificant deviation transformed a robust, protective design into a point of critical vulnerability. A wire under constant tension, particularly one rubbing against the metal edges of a powerful hydraulic system, was an invitation to disaster. The insulation, though robust, was not designed for such abrasive contact. Over time, with the repeated opening and closing of the bomb bay doors, actions that generated immense friction against the cold, high-speed airstream, that insulation would inevitably chafe, fray, and eventually wear through. When the copper conductor inside became exposed, it would be only a matter of time before it made intermittent contact with the grounded metal structure of the aircraft. In the confined, potentially fuel-vapor-laden environment of a bomb bay, even a microscopic spark could have catastrophic consequences. He knew that residual vapors of high-octane aviation gasoline, inevitably present in small quantities due to minor leaks from wing tanks or fuel lines, could accumulate. A spark in such an environment was a death sentence. This chilling discovery occurred against a backdrop of increasing anxiety within the Allied Strategic Bombing Command. Since January 1943, the United States 8th Air Force had been relentlessly pursuing its objective, the precision daylight bombing of German industrial targets, a strategy fundamentally different from the Royal Air Force's nocturnal saturation raids. The price for this daylight strategy was astronomical. From August to October 1943 alone, the 8th Air Force had endured the loss of over 200 B-17s over enemy territory, with casualty rates on individual missions sometimes soaring to a devastating 20%. Losses to formidable German Luftwaffe fighters and the relentless flak from 80mm anti-aircraft guns were known, brutal, and accepted risks of combat. However, a more insidious and deeply unsettling problem had begun to emerge. Fragmented reports trickled in from various bomb groups between June and October 1943. Aircraft exploding suddenly without warning, during or immediately after the release of their bomb loads. There were no enemy fighters, no obvious flak hits, no prior mechanical distress signals. These weren't cripples struggling back from a mission. These were flying fortresses disintegrating into orange fireballs, their wreckage raining down over the French and German countryside, leaving behind only perplexing questions and an eerie silence on the radio. These unexplained losses were a source of profound bewilderment and growing dread, creating an invisible, unidentifiable enemy that preyed from within the very machines meant to deliver victory. Crews, already facing horrifying odds in direct combat, now harbored a gnawing suspicion that their own aircraft could betray them. On October 15th, Parker meticulously documented his findings. His technical report was detailed, precise, and devoid of embellishment. He described the abnormally tense electrical harness, PN 43217C, within the bomb bay compartment, deviating from specified routing due to insufficient length, approximately 3 inches short. He noted its dangerous proximity to the hydraulic door mechanism and requested an immediate inspection and rectification procedure for all B-17F and B-17G aircraft within the group, particularly those recently delivered from the Boeing Seattle plant. He submitted the report through the proper channels, a routine act in the constant bureaucratic churn of a wartime air base. However, in the high-stakes environment of 1943, where the focus was on maximizing sorties and replacing combat losses, Parker's report was deemed a minor manufacturing anomaly, not an urgent safety threat. The administrative offices were perpetually inundated with reports of battle damage, engine failures, and structural fatigue. A technical sergeant's concern about a few inches of wire seemed, to those prioritizing the relentless demands of the strategic bombing campaign, a triviality. His requisition was subsequently filed away, overshadowed by the immediate imperatives of war. The vast anonymous machinery of the military bureaucracy, designed for efficiency, inadvertently masked a critical flaw through its sheer scale and the overwhelming pressure of wartime exigencies. For Parker, the filing of his report was not a dismissal of his work, but merely a delay. He had identified a silent, invisible killer that now haunted the skies of Europe, an enemy more insidious than any fighter squadron or flak battery, because it resided within the very machines that carried the hopes of the Allied war effort. His quiet resolve, a hallmark of his Midwestern tenacity, solidified. The danger, though unacknowledged by the command, persisted, a ticking clock within every B-17 still flying with the deadly unseen flaw. The unexplained explosions continued, a horrifying testament to a problem that was, for now, ignored. Despite the filing of his technical report, Raymond Parker remained unconvinced that his discovery would receive the urgent attention he believed it warranted. The pervasive wartime directive to keep him flying often meant that anything not immediately affecting an aircraft's ability to take off and deliver its payload was relegated to a lower priority. But Parker's Midwestern tenacity, a characteristic rooted in a lifetime of practical problem-solving, would not permit him to dismiss the potential danger. He had witnessed too many instances where a seemingly minor flaw in a piece of farm machinery could lead to a complete breakdown, and the stakes here were infinitely higher. The nagging question of the unexplained losses that plagued the 8th Air Force continued to haunt him, and his intuition told him his short wire was connected to the mystery. Refusing to let the issue rest, Parker initiated his own informal investigation. With the relentless rhythm of combat missions dominating daylight hours, his opportunities were limited to the long, cold night shifts. These were the hours when most crews were either preparing for the next day's dawn raids or recuperating, and the hangars, though still busy, offered a degree of quiet for focused work. Armed with his flashlight, a small set of hand tools, and a meticulous notebook, Parker began to systematically inspect every B-17F and B-17G he could access. He would crawl into the narrow, often claustrophobic bomb bays, his breath fogging in the frigid air, sometimes for hours on end. The work was arduous. The bomb bays were cramped and dark, smelling of hydraulic fluid, metal, and the lingering acrid scent of aviation fuel. Parker often had to contort his body into uncomfortable positions, his flashlight beam his only guide, as he methodically checked each wiring harness. His fingers, now accustomed to the precise contours of the B-17's internal anatomy, traced the path of the critical bomb release cable, searching for the telltale tension he had first identified. He wasn't just looking for the short wire. He was looking for the consequences of its installation. Over the next 11 days, Parker's methodical search became an obsession. Each night, as other mechanics completed their routine tasks or took brief, exhausted breaks, he would disappear into another bomber's belly. The records he kept in his notebook were a testament to his dedication. Aircraft serial numbers, dates of inspection, specific locations of the wiring harnesses, and detailed observations of their condition. Page after page filled with his neat, precise hand. His diligence yielded increasingly alarming results. Out of the dozens of B-17s he painstakingly inspected, he identified 37 aircraft with the identical manufacturing defect. The bomb release wiring harness was consistently 3 inches too short, forcing it out of its protected conduit and against the bomb bay door mechanism. But the mere presence of the short wire was only the beginning of his grim discoveries. In many of these 37 aircraft, the insulation on the taut wire already showed significant signs of degradation. He found wires with insulation that was scuffed, deeply grooved or abraded, the protective rubber casing worn thin in places where it had repeatedly rubbed against the metal edges of the bomb bay doors. The pristine factory appearance he had observed on the first B-17 had given way to undeniable evidence of wear and tear, a silent testament to countless hours of flight and repeated bomb runs. More critically, in 6 of these aircraft, Parker discovered distinct, small burn marks on the metal structure adjacent to the exposed sections of the wire. These were not scorches from external heat. These were arc marks. They were indisputable evidence of electrical discharge, miniature lightning bolts that had jumped from the compromised wire to the grounded airframe. Each arc mark was a chilling indication that electricity had at some point escaped its intended path, creating a spark. These were not just theoretical dangers, they were near catastrophes, moments when an aircraft had come terrifyingly close to exploding. For Parker, these marks were postponed executions, a stark validation of his initial fears. The mechanics of this defect were subtly insidious. The B-17's electrical system operated at 28 volts, sufficient to ignite flammable materials under the right conditions. The specifications from Boeing were clear. The bomb release wire was to be routed through a series of rubber grommets and metal conduits, isolating it completely from any moving parts or sharp edges. The 3-inch shortfall in the wire's length, however, violated this fundamental engineering principle. When installed, the wire was stretched to its limit, forcing it to bypass its protective routing and press directly against the frame of the bomb bay doors. During normal flight, the constant vibrations and subtle structural flexing of the B-17 caused the wire to rub incessantly against these metal edges. Over time, this continuous friction began to degrade the wire's insulation. However, the most critical stress occurred during a bombing run. As the bombardier activated the bomb release sequence, the massive hydraulic doors of the bomb bay would swing open with immense force, battling the intense aerodynamic pressure of the bomber's speed at altitude. The doors then closed, only to open and close again on subsequent passes or for later missions. Each cycle of opening and closing amplified the friction, effectively grinding away at the already compromised insulation. The cold, high-altitude air exacerbated the brittleness of the rubberized insulation, making it more susceptible to cracking and wear. The environment within the bomb bay itself compounded the danger. Despite rigorous maintenance, small, almost imperceptible leaks from fuel lines, wing tanks, or even the bomb arming mechanisms themselves meant that residual vapors of high-octane aviation gasoline were almost always present. These vapors, heavier than air, would accumulate in the confined spaces of the bomb bay, creating an atmosphere ripe for ignition. The moment the insulation finally wore through, exposing the live copper conductor, any contact with the grounded metallic structure of the aircraft would create an electrical arc, a spark. In that fuel-vapor-rich environment, a spark was all that was needed to turn a majestic flying fortress into a catastrophic explosion, disintegrating the aircraft and its 10-man crew in an instant. Parker's methodical inspection and the evidence of arc marks provided a chilling, logical explanation for the unexplained losses. It was not enemy action or unknown mechanical failures. It was an inherent design flaw, a silent killer manufactured into the very fabric of the aircraft. Each arc mark he discovered was a near miss, a testament to sheer luck and an urgent warning that the current run of good fortune could not last. The fate of hundreds of airmen and millions of dollars worth of vital war material hinged on a single short wire. Parker knew that without immediate intervention, it was only a matter of time before luck ran out for another B-17 and its crew. His quiet obstinacy had unearthed a truth that the vast machinery of war had so far tragically overlooked. The morning of October 26, 1943, dawned with a familiar chill over the airfields of eastern England. 88 B-17 flying fortresses of the United States 8th Air Force were tasked with striking the critical ball-bearing factories in Schweinfurt and Bremen, industrial targets deemed vital to the German war machine. The missions were known for their extreme danger, often involving relentless assaults by Luftwaffe fighters and dense barrages of flak. This day, however, would add a new, terrifying dimension to the already grim statistics of aerial warfare. Among the formations streaking eastward was the B-17G, serial number 4231034, known to its crew as Lucky Strike. Piloting the bomber was Captain Thomas Brennan, a seasoned officer whose steady hand had brought his crew through multiple harrowing sorties. Beside him in the co-pilot seat was Lieutenant James O'Malley. In the bombardier's position, peering through the Norden bomb site, was Lieutenant Howard Mitchell, whose precision was paramount to the mission's success. The 10 men aboard Lucky Strike were part of the 390th Bombardment Group, one of the many units relentlessly pushing the Allied strategic bombing campaign deeper into German airspace. The journey to Bremen was arduous, marked by intermittent flak and the constant vigilance against fighter attacks. As the formation approached the initial point, IP, the precise geographical landmark from which the bomb run would commence, the flak grew thicker, blossoming into angry black flowers across the sky. Captain Brennan maintained the aircraft's course and altitude with unwavering resolve, holding Lucky Strike steady despite the buffet of near misses. Lieutenant Mitchell, in the transparent nose compartment, began his intricate dance with the Norden bombsight, aligning the aircraft for the perfect release. At 11:37 a.m., over the industrial heart of Bremen, Mitchell called out, "Bombs away." The rhythmic thud of 4,000 pounds of high-explosive bombs detaching from their shackles echoed briefly through the fuselage. The aircraft, suddenly lighter by 2 tons, lurched slightly upwards. The objective was met. The payload was on its way. Immediately, Mitchell's voice, sharp with relief and urgency, came over the intercom. "Bomb doors closing." It was at this precise instant, as the massive, hydraulically operated bomb bay doors began their powerful sweep to seal the aircraft's belly against the furious slipstream, that the silent killer, long hidden, finally manifested itself. The defective wiring harness, the same type of 3-inch short cable Raymond Parker had meticulously documented at Thorpe Abbotts, had been under constant duress. For 20 prior missions, this particular wire on Lucky Strike had been stretched taut, rubbed raw against the metal edges of the closing doors. Its insulation, once pristine, was by now completely worn through, leaving the live copper conductor exposed. As the doors commenced their closing motion, the exposed wire, caught in the friction and movement, made direct sustained contact with the grounded metallic structure of the bomb bay. The 28-volt current, designed to activate solenoids, found an unintended path. The resulting electrical discharge was not sufficient to trip a circuit breaker or blow a fuse. It was, in the context of the aircraft systems, a microscopic event. But in that exact moment, the bomb bay was an environment primed for catastrophe. During the bomb run, despite strict protocols, the sheer violence of combat flight and the inherent complexities of the B-17's fuel system meant that minute quantities of residual high-octane aviation gasoline vapors inevitably accumulated within the confined space. These vapors, heavier than air, lingered, invisible and odorless, awaiting an ignition source. The microscopic spark generated by the short circuit was precisely that source. The explosion that followed was not a gradual event, but an instantaneous, cataclysmic detonation. From the perspective of the trailing aircraft, Lucky Strike simply ceased to exist as a coherent machine. A blinding, searing white-blue flash erupted from the midsection of the bomber, followed by a concussive shockwave that momentarily buffeted other aircraft in the formation. The sound, for those close enough to register it over the roar of their own engines, was a deafening, tearing shriek of metal, a sound that quickly dissolved into the chaotic silence of disintegration. Co-pilot Lieutenant James O'Malley was seated in the cockpit, his attention on maintaining formation, when the world around him was suddenly, brutally annihilated. There was no warning, he would later recount. No alarm, no strange noise, just a blinding white-blue flash from behind, and then the nose of the aircraft started to drop away. The force of the explosion tore Lucky Strike in half, roughly at the bomb bay. The tail section, still mostly intact but severed from its control surfaces, pitched wildly, tumbling out of formation. The cockpit and forward fuselage, now a rudderless, weightless projectile, began an immediate, uncontrolled plunge towards the earth. "Everything happened in maybe 3 seconds," O'Malley stated, "from the flash to realizing we were falling. In the immediate chaos, amidst the tearing metal and rushing wind of the disintegrating aircraft, survival was a matter of instinct and improbable luck." O'Malley, stunned but not incapacitated, felt the violent lurch of the cockpit as it separated. His training kicked in. He knew the aircraft was lost. With a desperate surge of adrenaline, he unclipped his oxygen mask and headset, unbuckled his seat harness, and fought his way through the collapsing structure. The air was frigid, thin, and screamed past him. He managed to force himself out of the rapidly falling section of the fuselage, battling against the extreme G-forces and the wind blast. He pulled the ripcord. The parachute blossomed above him, a sudden, jarring deceleration that ripped him upwards, away from the spiraling debris of what had moments before been his aircraft. Another crewman, whose identity remained obscured in the subsequent reports due to the chaos, also managed to bail out. These two would be the sole survivors of the 10-man crew. Captain Brennan, Lieutenant Mitchell, and the remaining 6 crew members perished instantly in the blast or in the subsequent uncontrolled fall. Lieutenant O'Malley descended through the cold German sky, landing hard in a field near Hanover. He was quickly captured by German ground forces. For the remainder of the war, he endured the harsh realities of a prisoner of war camp. It was not until after his liberation and repatriation that O'Malley provided his detailed debriefing. His account was chillingly consistent with the unexplained losses that had plagued the 8th Air Force. He described no enemy fighters, no flak hit, no mechanical malfunction that led to the event, only the sudden internal, white-blue flash that instantaneously tore his B-17 apart. This testimony, collected months later, would become a crucial piece of evidence indirectly confirming the grave dangers Raymond Parker had warned about. The unexplained mystery now had a harrowing eyewitness account, demanding a formal investigation into the true cause of these terrifying mid-air disintegrations. The tragedy of Lucky Strike was not an isolated incident. It was a desperate signal, finally too loud to ignore. The catastrophic loss of Lucky Strike on October 26, 1943, was the final, undeniable catalyst. The pattern of unexplained losses, aircraft disintegrating without apparent cause, had escalated from a troubling anomaly to an urgent crisis. The horrifying eyewitness account of Lieutenant James O'Malley, the co-pilot who had miraculously survived the mid-air explosion, eliminated any lingering doubts that these incidents were merely combat casualties. His testimony of a sudden, internal flash provided a crucial, albeit terrifying clue that demanded immediate and thorough investigation. The military hierarchy, which had previously relegated Raymond Parker's warnings to a bureaucratic file, could no longer ignore the mounting evidence. Major Robert Henderson, the flight safety officer for the 100th Bombardment Group, was immediately tasked with leading the preliminary investigation. His role was paramount, to gather every conceivable piece of evidence from the crash site, despite the immense logistical and wartime challenges. German ground forces had quickly secured the area around Hanover, where the main wreckage of Lucky Strike had fallen. However, Allied intelligence, leveraging both reconnaissance flights and resistance networks, managed to collect crucial fragments. These were not large sections of the aircraft, but rather smaller, often charred, pieces of the bomb bay and adjacent fuselage, recovered under perilous circumstances. Henderson understood the extreme urgency. These fragments represented the physical manifestation of the mystery, and their analysis was critical to identifying the invisible enemy. Within days of the Lucky Strike incident, Major Henderson embarked on a clandestine and perilous journey. Evading enemy patrols and navigating a continent at war, he transported the recovered fragments, secured in reinforced crates across the Atlantic. His destination was Wright Field, Ohio, the primary engineering and testing center for the United States Army Air Forces. This was where the nation's foremost aeronautical engineers and materials scientists worked, often in secrecy, to solve the most complex technical challenges of wartime aviation. Upon his arrival at Wright Field, Major Henderson presented his findings and the recovered debris to Colonel Clarence Irvine. Colonel Irvine, a man known for his incisive intellect and pragmatic approach to engineering problems, headed the Air Force Material Command's Specialized Accident Investigation Unit. His team consisted of a select group of engineers and metallurgists, experts in the forensic analysis of aircraft failures. The briefing Henderson provided, detailing the suddenness of the explosion and Parker's earlier, dismissed report of a short wire, immediately piqued Irvine's scientific curiosity. The unexplained losses now had a plausible mechanical theory. Under Colonel Irvine's direction, his team initiated a rigorous scientific investigation. Their first task was to recreate, as accurately as possible, the specific environment of the B-17 bomb bay. Using detailed blueprints of the B-17F and B-17G models, they constructed a full-scale mock-up of the bomb bay compartment in a specialized laboratory. This mock-up incorporated the exact dimensions, materials, and operational mechanisms of the actual aircraft, including the hydraulic system for the bomb bay doors and the complex routing of electrical harnesses. The goal was not merely to replicate the structure, but to simulate the dynamic conditions of flight, particularly the extreme stresses experienced during bomb release. The analysis began with the recovered fragments. Metallographic analysis was performed on the charred and twisted pieces of metal and wiring. Under high-powered microscopes, the scientists examined the microstructure of the materials for telltale signs of intense, localized heat and electrical discharge. They specifically sought evidence of arc damage, microscopic craters and resolidified metal droplets that indicate where an electric current had jumped from one conductor to another, or to a grounded surface, generating an explosive spark. The results were conclusive. The fragments showed clear and unequivocal signs of internal electrical arcing, consistent with a high-energy spark in a volatile environment. Next, the engineers turned their attention to the bomb release wiring harness itself. They obtained samples of the specific electrical cable, PN43217C, which Raymond Parker had identified. In the laboratory mock-up, they deliberately installed a wire of the same defective, 3-inch shorter length. They then subjected this setup to repeated cycles of bomb bay door opening and closing, simulating the conditions of actual combat missions. Electrical continuity tests were continuously run on the wire. As the simulated cycles accumulated, the results became chillingly clear. Just as Parker had theorized, the taut wire, forced out of its protected path, began to chafe against the moving edges of the hydraulic door mechanism. The insulation degraded visibly, thinning and eventually tearing. Within a relatively short number of cycles, far fewer than the 20 missions Lucky Strike had flown, the copper conductor was exposed. At that critical juncture, with the insulation compromised, the wire made intermittent contact with the grounded airframe, generating sparks. These sparks, even minute ones, were more than sufficient to ignite simulated fuel vapors introduced into the test environment. The scientific validation was complete. Raymond Parker's persistent observations, initially dismissed as the anxieties of a junior mechanic, were now conclusively proven by the highest echelons of Air Force engineering. The unexplained losses now had a definitive, terrifying explanation. The implications of these findings were profound and immediate. Colonel Irvine understood that this was not an isolated incident confined to a single bomb group. It was a systemic failure. An emergency review of Boeing's meticulously kept production records was immediately ordered. This was a monumental task, involving the rapid analysis of manufacturing logs, subcontractor details, and assembly line manifests, all under immense pressure. The review focused specifically on the period between June and September 1943, the time frame during which the defective batch of wiring harnesses was believed to have been introduced into the production line. The results of this urgent review sent a shockwave through the highest levels of the Air Force Command. Approximately 900 B-17 Flying Fortresses had been manufactured using the defective batch of wiring harnesses. The scale of the problem was staggering, far exceeding anyone's worst fears. These 900 aircraft were not confined to a single airbase or a single theater of operation. They were spread across the globe. 470 B-17s were already in active service in Europe, flying daily missions against the German war machine. Another 230 were deployed in the Pacific Theater, engaged in critical operations against Japanese forces. The remaining aircraft were still stateside, either in training bases, preparing new crews for combat, or awaiting deployment. This revelation exposed the terrible magnitude of the threat. Nearly 1,000 Flying Fortresses, each costing $250 US to manufacture, and carrying a 10-man crew trained at a cost of $50 US per man, were flying with a ticking time bomb hidden within their bomb bays. The war machine, designed for overwhelming force, was being silently undermined from within by a critical, yet invisible manufacturing flaw. The unexplained losses could now be projected to reach catastrophic levels if immediate action was not taken. The problem was no longer a theoretical risk or a local anomaly. It was a systemic vulnerability that threatened the very efficacy of the Allied air campaign. The urgency of the situation became undeniably clear. A massive, unprecedented logistical and engineering effort would be required to avert a potential industrial disaster of epic proportions. The scale of the threat, confirmed by the chilling analysis at Wright Field, demanded an immediate and unprecedented response from the Allied High Command. On November 4, 1943, a mere 9 days after the catastrophic loss of Lucky Strike, the United States Army Air Forces issued Technical Directive 43-1156. This directive bypassed normal administrative protocols, ordering the urgent inspection and, if necessary, the immediate replacement of the defective electrical harnesses in all affected B-17F and B-17G aircraft. The priority shifted dramatically. Every available resource was to be channeled into this critical safety operation, effectively pausing other, less urgent maintenance tasks. To spearhead this immense undertaking, Major Robert Henderson, who had championed the investigation, recognized the indispensable expertise of Technical Sergeant Raymond Parker. Parker's initial unheeded warnings had been tragically validated, making his hands-on understanding of the defect critically valuable. In an extraordinary move, Parker, the 23-year-old Iowa mechanic, was swiftly promoted to Master Sergeant and assigned as the technical supervisor for the entire rectification program across all 8th Air Force bomber groups in England. This rapid ascent was a direct acknowledgement that the quiet mechanic, whose observations had been initially overlooked, now held the key to preventing further devastating aircraft losses. Parker personally established training centers, instructing over 100 mechanics from various units on the precise inspection and replacement procedures. He demonstrated with his characteristic methodical approach how to identify the 3-inch short wire, recognize the telltale signs of chafed insulation, and interpret the subtle arc marks that signaled a near catastrophe. His teachings were not merely technical. They imbued in the mechanics a profound understanding of the lives that literally hung in the balance with each inspection. The rectification program became a logistical and engineering challenge of monumental proportions. Each replacement of the faulty wiring harness was an intricate operation, consuming approximately 8 hours of specialized labor per aircraft. Mechanics were required to partially dismantle sections of the bomb bay, carefully extract the old taut harness, install the new correctly dimensioned cable, conduct rigorous electrical continuity tests on all circuits, and then meticulously reassemble the compartment. This work was executed under relentless pressure, with teams working grueling 20-hour shifts, often illuminated by floodlights against the biting cold and damp of English November nights. High Command continuously pushed for speed, balancing the imperative for safety with the critical need to maintain operational readiness for the ongoing bombing campaign. Master Sergeant Parker, himself tirelessly overseeing the operations, meticulously documented every aircraft rectified in his weekly reports to Major Henderson, recording serial numbers, inspection dates, the condition of the old wires, and detailed observations on wear patterns, creating an invaluable database of the defect's progression. The statistics emerging from this mass inspection were alarming and stark. By the end of December 1943, of the 470 aircraft inspected in Europe, 193 exhibited significantly degraded insulation on the defective wiring harness. A further 87 had partially exposed copper conductors, a hair's breadth from a short circuit. Most chillingly, 21 B-17s showed clear, undeniable evidence of prior electrical arcing within their bomb bays, indicating that these aircraft had already experienced near-miss explosions, surviving only by sheer, improbable luck. Engineers at the Air Force Material Command, utilizing probabilistic models based on mission frequency and the observed conditions of the wires, estimated that without this emergency correction, between 150 and 200 B-17s would have suffered catastrophic explosions during combat operations in the subsequent 6 months. This translated to the potential loss of approximately 500 to 2,000 highly trained airmen and vital aircraft. Beyond the immediate material and human cost, the psychological impact on crews, already battling overwhelming odds against enemy fighters and flak, would have been devastating, potentially eroding their faith in their aircraft and crippling the strategic bombing campaign. The short wire incident served as a stark revelation of systemic vulnerabilities inherent in wartime mass production. Intense pressure to accelerate B-17 output had led Boeing to implement manufacturing changes without adequate engineering review. The defective wire batch originated from a complex multi-layered subcontracting chain where each link, a primary contractor, a secondary subcontractor in New Jersey, and an even smaller workshop in Connecticut, had made minor adjustments to specifications. These cumulative deviations, each seemingly insignificant on its own, resulted in the fatal 3-inch shortfall. In response, the Air Force Materiel Command established the Technical Bulletin System, a new, stringent protocol requiring all design or process modifications, no matter how small, to undergo formal engineering review, rigorous testing, and documented validation before mass implementation. This system, born directly from the short wire crisis, became the precursor for modern aerospace quality assurance programs, fundamentally transforming aviation safety protocols and standards across the industry. Raymond Parker's tenacity and the subsequent rectification efforts had profound and lasting repercussions throughout the strategic bombing operations. With the affected aircraft corrected, the unsettling unexplained losses plummeted to virtually zero, effectively eliminating a hidden killer and restoring crucial confidence in the B-17 fleet. Historians estimate that between November 1943 and May 1945, the period of the bombing campaign's greatest intensity, Parker's intervention and the massive repair operation saved between 180 and 200 complete crews, roughly 1,800 to 2,000 airmen, who would otherwise have vanished in explosions over enemy territory, their fates forever shrouded in mystery. After the war, Raymond Parker, a man of quiet conviction, returned to Iowa, resuming his life as a tractor mechanic in 1946. Though awarded the Bronze Star Medal for his extraordinary contributions, he characteristically shunned public recognition, insisting he was just doing his job. His meticulously maintained notebooks, now preserved at the National Museum of the United States Air Force, stand as a powerful testament to a fundamental truth of modern warfare. That victory often hinges not on dramatic battlefield heroism, but on the unwavering focus of individuals like Parker, who pay obsessive attention to seemingly trivial technical details, proving that one man's obstinacy can literally save thousands of lives and shape the course of history. The silent killer, once an unseen threat lurking within the very machines of war, was ultimately exposed. From the meticulous eye of a single mechanic, through the catastrophic loss of the Lucky Strike, to the relentless, round-the-clock efforts across freezing English airfields, a defect that began as 3 inches of missing wire was systematically eradicated. Raymond Parker's unwavering dedication not only salvaged an entire fleet from catastrophic internal failure, but resurrected the crew's faith in their flying fortresses. His obstinacy, born of a quiet Midwestern conviction, transformed a potential disaster into a profound lesson in systemic safety, saving an estimated 1,800 to 2,000 lives and forever altering the landscape of aerospace engineering. The legacy of Technical Directive 43 HUD 1156 and the technical bulletin system it spawned continues to underscore the critical importance of meticulous quality control, a silent guardian ensuring the integrity of flight. History often glorifies the thunder of cannons and the overt courage of pilots soaring through flak-filled skies. Yet, this narrative reveals a deeper truth: that the fate of nations, the survival of thousands, can hinge upon the smallest oversight and upon the quiet, unwavering resolve of an individual who dares to look closer. It is a testament to the overlooked heroism, found not in dramatic battlefield actions, but in the meticulous pursuit of technical perfection, where the most seemingly trivial detail holds the power to decide between life and annihilation. What seemingly insignificant detail in your own experience has held monumental importance, altering an outcome or revealing a hidden truth? Share your thoughts in the comments below. For more untold stories of the Second World War, Explore our collection of secret reports. And if the unwavering pursuit of truth in the shadow of war captivates you, consider subscribing to WW2 Secret Reports and leaving a like on this video to support our mission.